Okay, I'd like to welcome everyone here today to the Advancing Transformer Health Analytics Using Reliability Statistics on DGA. My name is Chelsea DeGay and I will be your host. Alongside me, I'm pleased to welcome Sean Casey, Director of Marketing at Deltax Research. With extensive experience in the software and technology sectors, Sean brings valuable insights into innovative strategies that drive industry growth. Also joining us is Jim Ducarme, Deltax Research's principal scientist and founder. Working full-time in the electric power industry since 1988, he has developed successful software products for monitoring and diagnostic applications, including widely used applications for factory switchgear monitoring, installation power factor testing, and dissolved gas analysis. Dr. Ducarme is a member of CGRA and a life member of IEEE. He is actively involved in the IEEE PES Transformers Committee Standards Development. Also, anyone joining today who may not know who we are, Deltax Research provides advanced decision support tools that help utilities and industry partners analyze transformer data. Our flagship products, Transformer Oil Analyst, or TOA, and newer product Monitor Watch, are used to manage and interpret test data for transformers that deliver half of the electricity consumed in the US. Today we will cover an overview of reliability-based DGA, history of DGA interpretation, current approach to DGA interpretation, gas limits, fault energy, hazard rate analysis, hazard factor, and validation case studies, everybody's favorite. Now over to you, Sean.
Thank you, Chelsea, and welcome everyone. Okay, so what is reliability-based DGA? Reliability-based DGA is a more accurate DGA interpretation method based upon relating transformer gassing to failures using reliability statistics. So the primary objective of reliability-based DGA is to provide early warning of fault-related gas production in order to avoid costly outages and prevent or limit equipment damage. So in this webinar, we'll answer some fundamental questions about a gassing transformer, such as when did the gassing start? How much energy did it take to make the gas? What does the gassing mean? And relatively speaking, how bad is this case of gassing compared to other ones in your fleet? So the IEEE C57-104 2019, so this is the IEEE Guide for Interpretation of Gases Generated in Mineral Oil Transformers, says DGA interpretation is still more of an art than a science. Being an art, if you're having trouble making sense of your DGA, you need to call in an expert. We consider reliability-based DGA to be that consistent scientific approach to DGA interpretation. So why is DGA so important? Well, 42% of transformer failures occur within the main tank and are detectable by DGA. So let's go through a brief history of dissolved gas analysis interpretation. So dissolved gas analysis, or DGA, is a widely used, effective, non-intrusive method for monitoring, periodic screening, and investigative diagnosis of power transformers. So until the 1960s, experts would actually sniff the transformer headspace gas to see if they could smell acetylene, which is a gas produced in extreme temperatures. So in the late 1960s, chromatography was introduced to DGA, allowing for individual problems related to gases in the transformer to be interpreted. So now that individual gases could be interpreted, the introduction of gas concentration limits was driven by the need for evaluating and assigning meaning to these gases. So gas concentration limits came about to try to answer the question of, are the gassing levels too high? And if so, should we investigate them? So gas concentration limits are still in use today, as we'll see throughout the presentation. So when we look at current approaches to DGA, the IEC and IEEE DGA interpretation guides assume the principle that more fault gas indicates greater risk of outage. They also employ percentile-based limits for concentrations, increments, and rates of increase for individual fault gases. So if any gas concentration in the latest oil sample exceeds a limit, investigation is needed. And DGA codes are applied to these gas limits. and it's worth noting that there is no quantitative risk metric applied. So ultimately, the rationale for DGA, including reliability-based DGA, is to discover fault-related gas production as early as possible, to do something about it to prevent potentially expensive deterioration, damage, or shortening the service life of the transformer. Okay, so we talked about the introduction of gas limits to assign meaning to individual gases. Now here are some of the issues with using gas limits for DGA interpretation. So there is no clear definition of how to select an appropriate interval for calculating gas increments and gas rates of change. There can be plus or minus 15% uncertainty or worse in gas concentration data. This noise makes it difficult for interpretation. And gas rates of change are based upon consecutive high noise samples. This is unreliable and prone to false alarms. So gas loss from the transformer or sample makes it difficult to detect, identify, and assess problems. Furthermore, applying statistical techniques to a gas limits-based approach has its own set of challenges. So high data percentiles are based on only the top 2, 5, and 10% of the data. And for that reason, they're very uncertain and they have poor repeatability. So the lower limits produce more false positives, whereas the higher limits produce more false negatives. So how do you optimize this? So these are some of the problems with gas limits. So when we look at DGA interpretation, it's a three-step process. And reliability-based DGA is only concerned with fault detection and severity. So this is the first and the third box in the diagram, the ones in turquoise. In gray, their fault identification, the middle box, is performed by what is known as the 4-simplex method at Delta X Research. Others would be familiar with the Duval triangle or pentagon. And the topic of fault identification won't be covered today, but it will be covered in an upcoming webinar. So we're going to look at what is the fundamental principle of DGA. So transformers are designed to function for a very long time without damaging or destroying the internal electrical insulation. Therefore, when insulation deterioration byproducts are being formed in a transformer beyond what is expected due to normal aging, then something is wrong. So what is reliability-based DGA? So it is a more accurate DGA interpretation method developed by Delta X Research, which is an evolutionary improvement addressing and fixing known problems with conventional DGA interpretation. Solving some of the problems such as how to cope with high noise level in DGA data, how to recognize and quantify ongoing fault gas production, how to deal with gas loss, and over what intervals to calculate increments and rates, and finally, how to quantify the severity of a problem. So reliability-based DGA interprets the same lab data and portable gas analyzer data as conventional DGA interpretation. And reliability-based DGA is the only DGA interpretation method that associates fault gas production with transformer failures. So an outline of reliability-based DGA interpretation is described in IEEE C57104 Annex F in the 2019 edition as an alternative method for DGA interpretation. Now we're going to look at fault energy. So fault energy is the energy that has been improperly diverted inside the transformer due to an internal problem. So fault gases are created when fault energy cracks the insulating oil or carbonizes the insulating paper. So a transformer oil chemist named Freddie Jacob realized that instead of tracking individual gases, it would be more useful to track normalized energy intensity. This represents the fault energy that went into creating the observed gases. So NEI, or normalized energy intensity, is calculated from individual gas concentrations and shows the onset and development of issues in the oil and the paper. So Delta X Research moved DGA interpretation from an art to a science by showing how NEI can resolve known difficulties in DGA and provides a valid statistical indicator of relative risk. And Annex F as well describes, in the IEEE C57104, describes how to use NEI for DGA. So NEI is a fault energy index used for trending and assessment of fault energy. So it can be challenging for engineers to interpret graphs of individual gases over time, as seen with the top right graph. Looks like a spaghetti graph. So simplicity of interpretation was one of the key reasons for the creation of a fault energy index. This is similar to that of a market index such as the Dow Jones. So an NEI index exists for both impacts of the oil, so these are the hydrocarbons, so NEIHC, and the paper, the carbon oxide, so this is NEICO. So either insulating material can generate hydrogen, while methane, ethane, ethylene, and acetylene are mainly produced by the oil, and carbon monoxide and carbon dioxide are mainly produced by the paper insulation. So the bottom right graph shows NEIHC, so this is impacts the oil, and the dotted line in this graph represents NEI calculated from raw values, whereas the solid line shows the accumulated, filtered, and smoothed NEI. So the fault energy index shows how bad problems are, this is the rate of change, and when chronologically they occurred. So significant gas events are shown with the red boxes, and this will become important when we look at the case studies. So the introduction of the fault energy indices to solve difficulties with conventional DGA was a major advancement in DGA interpretation. So now we're going to look at hazard rate curves. So Delta X research has a large population of thousands of transformers DGA data, including information on DGA detectable failures. And this was contributed to us by large North American utilities. And the goal was to look at how increasing fault energy indices relate to the likelihood of a forced outage due to an internal fault. So the hazard rate curve shows us the velocity of decay of the population at any gassing point. And that point gives us a corresponding hazard rate on the y-axis. So in these graphs represented on the x-axis is the accumulated fault energy impacting the oil. This is NEIHC. And on the y-axis is the hazard rate. And this is defined as a forced outage related to an internal defect or fault. So with the graph on the left, we're looking at hazard rate versus normalized energy intensity at a scale of 0 to 0.25 kilojoules per kiloliter. So it's really zoomed in on the initial gassing event. So at the onset of fault gas production, hazard rate goes up almost vertically, representing the risk of immediate failure. Then by about 0.05 kilojoules per kiloliter, which is still very low, the hazard rate levels off, indicating that by this point, additional gassing does not reflect additional risk. So the condition causing the gassing event isn't drastic enough to cause a defect or fault causing a forced outage. So it's the same graph on the right, it's just zoomed out to a scale, NEI scale of 0 to 1500 kilojoules per kiloliter. And this graph shows a sharp initial incline in the hazard rate, followed by a sharp decline, and then a very slight decline beyond NEI, approximately 100. So this again highlights that if the initial gassing does not lead to failure, additional gassing does not suggest increasing risk of near-term failure. So when a transformer starts to produce gas, this indicates that something is wrong, and in some cases that problem is bad enough to take out the transformer quickly. So the real lesson here is that the early stages of gassing, there's an opportunity to investigate or intervene and possibly save the transformer, and early detection and response is critical. Now we're going to look at hazard rate and limits-based approaches. So using a hazard rate model to see how DGA really works was a giant leap forward in understanding the deficiencies of conventional DGA interpretation. So in contrast with reliability-based DGA, with a conventional limits-based approach to DGA interpretation, not much attention is given until gassing has gone well past the hazard rate peak. So then more gas is believed to signify more urgency and more presumed risk of failure. So using reliability statistics, Delta X research showed that as we move down from the peak, the top of the curve, to status code 2, the 90th percentile, and then to status code 3, the 95th percentile, this corresponds to a lower hazard rate. So the IEEE higher level limits do not suggest higher levels of risk, exactly the opposite. The 90th percentile limits are too high for preventing some failures, while the 95th percentile limit falsely suggests higher risk. So the model shows that if the initial gassing is not due to a problem that kills the transformer quickly, additional gassing gradually declines in significance. So some of the highest rates of failure with gassing occurs before the 90th percentile level is reached, and potentially before you missed your opportunity to intervene on your multi-million-dollar investment and the opportunity to keep the lights on for your customers. So we can see this in the graph with the area shaded in orange, indicating the percentage of the population of transformers expected to experience a failure before the 90th percentile is actually reached. So during the initial gassing stages, the transformers start to fry their insulation, and by waiting for the 90th percentile to be exceeded, you forego the possibility of preventing or mitigating some failures. So it's worth noting that conventional DGA has been effective in the fact that a gassing transformer is by definition faulty, and therefore may not have the expected resilience and durability. So do we need to have 90th percentiles of NEI? No, because we're able to identify gassing transformers and quantify the relative amount of energy involved. So we're not doing art anymore, it's science. So after the introduction of NEI-HC, so this was the introduction of impacts to the oil, and based upon the fault-related carbonization of cellulosic insulation, so charring of the paper, Delta X Research introduced NEI-CO, which is for the impacts to the paper, and so it's NEI carbon oxide. So the NEI-CO hazard rate curve is a similar shape to NEI-HC, except that it rises less steeply, and because any deterioration of the paper is harmful to the transformer, does not go down as quickly. There is a lot of paper in a transformer, and there is a possibility of generating a lot of CO2 by means of mild overheating without a failure actually occurring. So in the case of significant carbon monoxide production, which is only formed above 500 degrees Celsius in the transformer, the NEI-CO increases dramatically, taking you further along the curve to an increased hazard rate. So because carbon monoxide and carbon dioxide represent different levels of severity, the NEI-CO hazard rate needs to be interpreted alongside the CO-CO2 ratio. This will actually be a topic of discussion for another webinar. So hazard factor is an analytic that helps quantify the risk of continued operation of a transformer should gassing continue. So hazard factor is actually the rate of destruction of insulating material. This is the NEI, or rate of increase, multiplied by the hazard rate. And we call this the how much do I care factor at any given gassing point. So hazard factor balances the rate of increase and the hazard rate in order to avoid panic-based false alarms. So hazard factor is a realistic DGA-based risk assessment because it rightfully gives more weight to rapid versus mild gassing and much more weight to recent gassing rather than old gassing. So for utilities using hazard factor, it provides a realistic risk of near-term failure for prioritizing your transformer fleet. So this greatly improves the ability to manage your fleet as a whole. So hazard factor should be considered a ballpark estimate of relative risk rather than a sharp quantity that one can bet lives or huge money on. So it's important to consider that hazard factor is based on statistical averages over a population. So there is no guarantee that a transformer with low hazard factor will be safe to stand next to, or that a transformer with high hazard factor won't last for another 20 years. So hazard factor is all about intelligently placing your bets. So although hazard factor may appear relatively low in some cases, early investigation is still critical, as we know from the earlier slides that gassing events are most dangerous to the transformer when they first emerge. So what can impact reliability-based DGA and DGA in general? Well, gas loss is the big one. So transformers leaking gas is not a rare occurrence, and gas loss can lead to late or no detection of problems and underestimation of severity. So when gas loss is due to health problems, it needs to be corrected in order for DGA to be effective. So to partially compensate for gas loss and preserve upward trends, reliability-based DGA ignores decreases and accumulates increases. So this is in order to preserve evidence of active gassing in spite of the gas loss. And the other big thing that can impact reliability-based DGA and DGA in general is poor DGA sampling practices. So if you lose gas from the oil samples in the transformer or in a test tube, it will introduce noise and inaccuracy into DGA measurements. Furthermore, collection of oil samples that are not representative of the bulk of the oil in the transformer, or careless handling introduces huge levels of variation in the data. So reliability-based DGA does perform smoothing to eliminate large random sample-to-sample variation. However, no amount of massaging the data can restore information that is lost or missing due to poor data quality. So let's look at some of the benefits of reliability-based DGA. So the main job of reliability-based DGA is simply to support taking good care of the fleet and supporting effective maintenance practices. And the key to this is to discover fault gas-related production as early as possible to prevent equipment damage and unplanned outages. So Jim Ducarme, our lead scientist and founder, told me a story about a customer that came to him and asked him to look at a particular transformer with his new reliability-based DGA method. So he ran the analysis, and it showed red boxes all over the place in the NEI graph, and the fact the transformer had been overheating for at least 20 years. So Jim told this customer, don't have lunch next to that transformer. So they called him back and said they had no idea the transformer was overheating, and if they would have known this, they would have replaced the fans 20 years ago. And Jim, believe it or not, the transformer exploded and burned down a residential substation. So Jim's method passed the test, and they said, please run our entire fleet through your method. And we'll see this in the validation study in the next slide. You can also think of reliability-based DGA as a more effective check engine light in terms of being timely, accurate, and as well as indicating severity of the potential issue. So transformers can fail in the early stages of gassing, and this is often missed using conventional DGA. So since you're dealing with an extremely valuable and important asset, early warning is critical. So now we'll move into validation. So now we'll look at a validation exercise we performed with a large North American utility. So again, the motivation for this validation was a transformer catastrophically failing and burning down the residential substation, even though conventional DGA showed no significant risk for the entire transformer's life. So the analysis of in-service DGA data and reliability-based DGA revealed a prolonged gassing event that was severely damaging the insulating components that actually caused the failure. So it was gassing because of purposeful overloading of this transformer, and it was actually masked by gas loss. And this was picked up by reliability-based DGA. So when we looked at the entire fleet, reliability-based DGA also helped the utility find 63 more in-service transformers that showed abnormalities that the utility was not actually aware of. So we'll look at this in a little more detail here in the next slide. So here are some of the key findings from the validation case study of 7,280 transformers with this utility. So conventional and reliability-based DGA flagged a similar number of transformers for further investigation. This was approximately 1,700. So the interesting part is there was not as much overlap as you'd expect. So 1,054 transformers flagged by conventional DGA that were not flagged by reliability-based DGA, and these were primarily false positives flagged by conventional DGA. So 998 transformers were flagged by reliability-based DGA that were not flagged by conventional DGA, and these were primarily misses by conventional DGA. So of the 998 flagged by reliability-based DGA only, the utility went in for further investigation on 68 of the in-service transformers. So 63 of them had confirmed abnormalities and 2 bad samples and 3 false positives. So what does this all tell us? Well, the utility could have used reliability-based DGA to discover problematic transformers that otherwise would have remained hidden with conventional DGA, and likely have saved the transformer that catastrophically failed. Also, the utility could reduce costly, unnecessary maintenance associated with a very large number of false positives that were introduced with conventional DGA. So this is why the validation effort led to the utility adopting reliability-based DGA in its infancy stages. So now we'll get into 3 case studies. So the first case study is a transformer that failed. So this transformer tripped due to a turn-to-turn arcing, and it was a complete surprise to the utility as the transformer never exceeded IEEE gas concentration or rate of change limit. So as a reminder, the red boxes show where significant fault gas production occurred. So when we look at the graphs, the hydrocarbon fault energy, the top graph, trend showed two distinct gassing events, which indicated thermal fault gas production. And there also is a long carbon oxide gassing event in the middle graph, which suggested continual thermal degradation of the insulating paper. So reliability-based DGA would have flagged the unit for investigation early on in the gassing events, well before the unit failed. And a post-mortem revealed extensive charring of the paper winding insulation. So our second case study here is an urgent replacement, not actually failed yet. So looking at the fault energy, we see the following. So as seen in the boxes of the first two graphs, so the top graph and the middle graph, the gassing events started in 2012, and it was actually a T2 hotspot, impacting both the paper insulation and the oil. And at the bottom graph there, with the CO2, you can see the percentage increase was extreme during this time in 2012. And this suggested the winding paper was affected. So the gas evidence of the problem actually dissipated beyond 2012. You can see they flatten out as the fault gas lowered. However, in 2018, we see another spike, and this is an electrical discharge appeared. And you can see this in the hydrocarbon fault energy in the top graph most dramatically. So upon reanalysis, reliability-based DGA revealed that clearly the transformer was in precarious condition and highlighted the need for replacement, even though the IEEE status code was only elevated to a status code 2 in 2012 and returned back to a 1 because of the gas loss. Okay, and our last case study here is another transformer failure. So between 1996 and 2013, there was a long, steady trend of fault gas in both the paper and the oil. You can see this in the top and middle graph. In 2013, the hydrocarbon fault energy trend accelerated sharply, indicating an issue. And the acetylene production produced a fault type of D1. So this is a low energy electrical discharge, although all other gases remained below the IEEE limits. So later the acetylene dissipated as the original trend resumed, with no conventional DGA thresholds exceeded beyond 2013. So the unit failed in 2018, but the transformer never reached IEEE status code 3, except for the initial spike in acetylene during the 2013 event. So with reliability-based DGA, the fault gas production identified a high risk T2, this is between 300 and 700 degrees Celsius, alert to the unit around the 2014 to 2015 time period, well before the unit failed in 2018. So if you're interested in following up with us as part of the consultation process with new customers, we'll actually take in past DGA data from select transformers and show how reliability-based DGA would have produced results. So in today's discussion around reliability-based DGA, we looked at fault detection and fault severity in the DGA three-step process. So in the next webinar, we plan to talk about the 4-simplex method of fault identification, and we can really consider it a next generation Duval triangle. So thank you everybody for taking the time today, and now we're going to move into the Q&A portion of the session.
Thank you, Sean, for that wonderful presentation. Just a reminder to anybody who came in late, if you have any questions, you can go to the top right-hand corner with the question mark, put your question in there. Also, I didn't mention at the beginning, there's a little paperclip icon. There you can find a DGA guide and also a TOA brochure and monitor watch brochure. Okay, just looking here. Okay, we have a couple questions. Okay. Okay, Jim, we got one question here. Does this only detect transformers about to fail?
No, it doesn't. What R-DGA does is detects fault gas production. So As the hazard rate graph showed, gas production can actually go on for decades without failing the transformer. But by definition, since the transformer is designed not to cook itself during normal operation, when you start seeing signs of insulation degradation, in particular fault gas generation, by definition, the transformer is not doing right, and you need to check it out. Because as Sean showed, the way the hazard rate graph goes, the hazard rate goes from 0 to its maximum, like very quickly in the initial stages of graphing, gassing, not graphing. Um, so that tells us that, there are, not all, but there are some cases where the transformer is saying, hey, I'm in trouble. And then you might have, a day or a week to find out what's going on and intervene before the thing blows its top. If it doesn't do that, well, then the transformer may be still damaging itself inside, more or less, and you won't know until you do some offline testing what's going on in there. So it's Sean mentioned the check engine light. This is a very good analogy to DGA. DGA is really a check engine light. R-DGA is a special check engine light that mostly only comes on when there's actually a real problem. And the brightness at which it glows tells you how scared you should be. So, if you're driving down the road in your brand new Ferrari or pickup truck or whatever it is, and the check engine light goes on, like, what happens? You get a nauseating sensation in your stomach, which is very appropriate, and you probably pull over, right? Go look under the hood or whatever you can do. But only an idiot would just continue barreling down the highway full speed with the check engine light on, not knowing what it is. Because there's a chance that you're going to end up with a windshield full of oil and you're going to go off the road. Or not. You may get to the next town and find out that, gee, if you'd only stopped, you could have, saved yourself from $3,000 worth of damage. Same logic applies to the transformer. When you see fault gas production, that's the check engine light. And R-DGA is just simply a better check engine light.
Okay, thank you. So Brian, we got a question. Have you data on DGA related to instrument transformers, HVCTs, or HVVTs?
I'm sure we do, but for purposes of this analysis, we didn't. We didn't get into that kind of detail. Really, in the population that we analyzed, which was something like 10,000 transformers, there were only a few hundred failures. The transformers are way too reliable in order to, to have lots of fun with this analysis. So if you were to narrow down to like the 75 or so histories we have for instrument transformers, you probably wouldn't have any failures to work with in that group, or not, at least not enough to draw conclusions from. So we're still, once we've gotten everybody's interest with this and they realize the usefulness of failure data, we hope that we'll get more contributions from TOA users, and we'll be able to sharpen the statistics and maybe specialize to a few types. I don't know about instrument transformers, but say GSUs versus, rectifiers or something like that.
Okay. Thanks. Thank you. Steve, what is the cost difference between just using TOA and TOA with monitor watch? I will direct you to Kayla. I have her information on the right-hand side here. She'll be able to give you more in-depth cost difference with
Could I
that.
just poke in here a comment?
Yep.
Unlike limits-based DGA, R-DGA works just the same way without any changes except in the signal processing with monitor data versus annual sampling data. This is sort of an indication of the validity of the approach. If you try to apply fixed limits to monitor data, you get false alarms all over the place.
Okay. And John, how does this technology help me set maintenance or replacement priorities in changing my transformer fleet?
Well, knowing which transformers are behaving abnormally is a good start. You have the hazard factor, which is our statistically based risk indicator, which you can multiply by cost factors and things if you want true risk, with the caveat that in the case of gas loss, if the transformer is losing gas, the hazard factor will be a very, possibly very much lowball estimate of the risk. So, you have to look at the individual transformer and say, do I take the hazard factor as is, or do maybe I boost it up some because I know that this transformer has a bad gasket, or that it's a nitrogen pressurized unit that frequently sheds headspace gas or something like that, So it's a start, I would say, but it's not like an off-the-shelf, use it as it is solution for that particular problem.
Okay. Another question from Jean. How are smaller transformers analyzed? How does the analysis method change if the transformer has a much smaller volume of fluid in the main tank? Does the gas limits or maximize rate of change?
Well, since we're not bound to any kind of limits, there's nothing of that sort. I know from having been there and gotten the IEEE T-shirt that this is a concern in discussions of conventional DGA, like how should we have a different database for small transformers, blah, blah, blah. But since we're not concerned with limits whatsoever, really the main thing that all this is based on is the bare fact that the transformer is gassing and it shouldn't be, right? So if it's a small transformer and it's, got a 500-degree hotspot in it or something, and so it's generating ethylene or whatever, that is a problem. And if it's a 500-gallon transformer instead of a 50,000-gallon transformer, it's still the same thing going on. So the short answer, which it's too late for, to your question is, no, the analysis isn't any different for small transformers versus large ones. If we had a large enough database that we could afford to do the survival analysis on small transformers, it might turn out that there would be some differences of scale in the hazard rate curves or something like that. I don't really know. But since we don't pretend that the hazard rate is a sharp-edged, bet your life on it tool, it's a relative indicator of risk. And so I'm very confident that as that, it works pretty well for small transformers. Again, the principle is the transformer gassing or not? And then the question is, when did it start? And how fast is it gassing? And that's pretty much going to work in any oil-filled transformer.
Okay. Another question from Paul. How does oil vacuum processing influence NEI data interpretation?
Um, the, well, that will zero out all the gas concentrations, at least momentarily, in the transformer. So, say if you do have an upward trend going on because the transformer's, overheating something, then you degas the transformer. You'll see a step down in the trend graph of the NEI, and then you'll see that the original trend resume. So, assuming that you haven't repaired the transformer, so it's just like a break in the trend graph. And our analysis uh, includes, because we're only looking at increases and not decreases, and we have some logic to detect like explicitly degassing events. Um, the NEI trend graph in that kind of case wouldn't break at all. It would just show us a trend going up, and the degassing wouldn't affect it. In conventional DGA, of course, all your numbers are reset to 0 and you're back to square one on limit comparisons.
Okay. Okay, another one. According to IEEE C57.104-2019, Table 1 through 3 reference the O2N2 ratio as an indicator. However, during the presentation, the focus appeared to be on CO levels. Are there additional gas indicators you recommend for monitoring paper insulation degradation?
Sure. Well, first of all, the O2N2 ratio consideration, which I was personally a supporter of when it first started, it seemed like a great idea. Um, there's a clear difference if you separate your database into transformers which on average have more oxygen versus transformers which on average have less oxygen in them for whatever reason. All those percentiles come out differently, so you do get different sets of limits. And in the working group, we all said, "Oh, goody! This is a great step forward." Well, it turns out, like the original intent was to separate transformers that may be exchanging gases with the atmosphere from the others. Problem is, in that massive population of transformers that have nitrogen regulated headspace pressure, where overpressure causes pressure relief, which means you're expelling headspace gas, and then under pressure, when the transformer cools off, causes the pressure to be made up by just admitting pure dry nitrogen. So in a hot place like the Southwest, where it can get murderously hot during the day, the transformers, they get hot and they expel gas, and then in the evening they cool off and you get the desert cold at night, and then you get nitrogen. So that whole process has the effect of pumping fault gas out of the transformer and also pumping oxygen out of the transformer. And so those transformers are very low oxygen, so they're in the low O2 over N2 group, but at the same time, they're losing fault gas to the atmosphere, so they should be in the other group as far as their limits are concerned. So we put our foot in it. And so Zach and I think, published a nice paper showing how you can determine the effective breathing type of a transformer from these gas ratios. And it shows the miserable failure of the oxygen-nitrogen ratio to do that. So oxygen-nitrogen, I would not recommend paying too much attention to that on the other hand, it has turned out that the carbon oxide gas ratio has gone from being a sort of an orphan child to being something extremely useful diagnostically. For years and years, we had sort of folk limits for that ratio, the carbon dioxide, carbon monoxide ratio, where you'd say, well, under 2.5, you probably have some kind of an electrical fault going on that's affecting paper. And over 10, you have like general overheating that's affecting the paper. But there are transformers that all the time, were running at a ratio of 2.5 or 10 or whatever. And so everybody would just sort of say, it's a ballpark criterion. There's a utility engineer who I think now works for another company dear to us, Chris Rutledge, who figured out that the thing to pay attention to is the percent change in that ratio, the percent change, not the value of it. And if you look at the percent change in the carbon oxide gas ratio, you can actually tell, A, is there a problem? And B, approximately where is that problem located? The change will tend to be very rapid and large if the fault is inside the winding, and it will tend to be less large and less rapid if it's, say, in a bushing lead joint or something like that outside the windings. So that's an incredibly useful diagnostic feature now. And in combination with tracking the NEICO, the energy related to the carbon oxide gases, we now have a really good handle on what's happening with the solid insulation. I hope in that rant I didn't forget the original question.
Yeah. Another one. Does this analysis method work also for FR3 transformers as well as mineral oil filled transformers?
This is a very timely question because I believe it was reported in the last Transformers Committee meeting, the C57-155 working group on ester fluid filled DGA for ester fluid filled transformers. Some really great organic chemists in that working group have come up with an adaptation to the NEI idea for ester fluids. And we are right at this moment doing the analysis for that. But I expect that we'll be able to pretty much reproduce the existing R-DGA method that we've worked out for mineral oil over the years. And it's going to apply in the same way. So in ester fluids, the chemistry is a little different, but there's still an energy-based index that you can trend. It works the same way as NEI for mineral oil, and it tells you all the same things. The survival analysis, of course, is going to be a little bit more sketchy because we don't have that many ester-filled transformers. We don't have that rich a history. But believe me, I'm working on that. So we'll have more to say probably at the fall Transformers Committee meeting.
Right. And from Matthew, when we manually sample a unit many times in a given year, we run into the same phenomenon you run into with online monitoring, where you need Monitor Watch to account for the frequent sampling and prevent false alarms. However, there seems to be no way to prevent these false alarms for transformers manually sampled frequently in a given year for units without online monitoring and the associated benefits of Monitor Watch. Can you Delta X create an upgrade to the R-DGA software to account for this in the same way that Monitor Watch accounts for via Monitor Watch?
Well, actually, I think we already have. the adaptations that we've made just for the normal periodic manual sampling type DGA of smoothing out, big, clearly random changes and accumulating positive increments and ignoring negative increments to get an NEI trend. That will work for manual sampling, even if, say, you're doing it weekly or maybe sometimes even daily. So I don't think we need to introduce any additional signal processing measures beyond what we've already got. Now, for straightforward out of the IEEE book limits-based DGA, then of course the existence of random ups and downs in the DGA data and the attention to individual gases as opposed to a composite is going to cause you tremendous grief. And yes, the more frequent sampling might amplify that. But for R-DGA, it shouldn't have any effect. It shouldn't have any bad effect, I should say.
Okay. Okay.
If it does, please let us know and we'll look at it.
Yeah. I think that's it. Well, thank you everyone for joining, all your great questions. Again, if you have any more questions you think of later, you're like, hey, I want to know this, again, on the screen, you can talk to Jim directly if you want to, or Sean. Again, thank you. Oh,
could I just leave you with one parting shot? That
yes.
link with the paperclip is to it includes our DGA guide, the Delta X Research DGA guide, in which all of these principles are explained in grinding but friendly detail. So please read that DGA guide. You'll find it very, very enlightening.
Perfect. Thank you. Okay. Thank you, everyone. Have a good day.